Hello. Uh, right now we're going to be going over a exam 3 from fall last year. Because fall last year the exam had more stuff with 6.5 and 7.1, 7.2. So I think that'll be better for review for this semester as well. So first off, question 1. We are solving the following nonlinear system: x squared minus 2y equals negative 5, and negative x plus y equals 4. So to solve this, I'm just going to use substitution. So I'm going to solve for y in the second equation. So y equals x plus 4, just by adding x to both sides. And then I'm going to plug that into the first equation. So x squared minus 2x plus 4 equals negative 5. And we can get x squared minus 2x minus 8 plus 5 equals 0. Just adding the 5 over and distributing. And then x squared minus 2x minus 3 equals 0. And let's see, it looks like here we can just factor this. So that's x. So two things that multiplied hit negative 3 and add to get negative 2. So 1 and 3. Since we're adding to negative 2, the negative number should be bigger. So x plus 1 and x minus 3. So x equals negative 1 and 3. Now we need to plug those back in to find out what the y value that corresponds with them is. So I'm just plugging back into the equation that we solved for y in the first place and go, let's see here, for x equals negative 1, we have y equals negative 1 plus 4 equals 3. And for x equals 3, we have y equals 3 plus 4 for 7. So now a lot of people will be tempted to just write x equals negative 1, 3 and y equals 3, 7. Well, that's not quite accurate. We need to make sure that they're paired. Remember that the negative 1 x equaling negative 1 means y equals 3. And x equaling 3 means y equals 7. If we just put negative 1 and 3 and then 3 and 7, then that gives us 4 possible solutions when we wanted these two specifically. So make sure you write these as ordered pairs. Okay, problem 2. Let's see, solve the given linear system following these steps. Let's see, there will be no solutions, infinitely many solutions, and so on. State y, show work. So first off, for 2a, we want to write the augmented matrix for the system. So remember, the augmented matrix is just pulling out the coefficients of everything. So first off, x plus y plus 3z, that's 1, 1, 3, 1. And then 1 minus 1, 2, negative 2, 1, 1, 4, 2. So I'll put that line just to separate left side from right side. So that would be our augmented matrix. Part 2 asked us to reduce it to be upper triangular. Upper triangular is the same thing as row echelon form. So we're going to use row operations. There are different ways of denoting row operations. This is what I do. I'm just saying that row 2, I'm changing it to be row 2 minus row 1. Then I'm going to say row 3, I'm changing that to be row 3 minus row 1. The way you do it doesn't have to be exactly the same, just make sure we can follow your work so we can actually grade what you're doing. So row 1 isn't changing, and row 2, we're subtracting row 1 from row 2 just so we can create zeros underneath the first entry. So 1 minus 1 is 0, negative 1 minus 1 is negative 2, see 2 minus 3 is negative 1, negative 2 minus 1 is negative 3. And then for row 3, same thing, we're just subtracting row 1 from it, so that's 0, 0, 1, 1. Okay, now technically this is row echelon form, it's upper triangular, since everything below the main diagonal is 0. Now we want to finish solving. We can either finish solving by making it reduced row echelon form, or we can just pull everything out of the matrix from here. I'm going to make it reduced row echelon form just because I like doing that more. So to do that, I'm going to make everything above the main diagonal 0, and then everything on the main diagonal has to be a 1. So I'm going to change row 1 now. Row 1 is going to be row 1 minus, row 1 minus 3 times row 3, and then row 2 is going to be row 2 plus row 1. So row 1, I am subtracting row 3 from it, so that's, so I haven't gotten the hang of this thing. Let's see, so that's 1, 1, 0, negative 2. And then row 2, I'm adding row 3 to it, so that's 0, negative 2, 0, negative 2. Row 3 isn't changing. Okay, then I want to make row 2. I want to make that a 1, so that's negative 1/2 row 2. And then after that, I'm going to make row 1 is going to be row 1 minus row 2. So row 3 isn't changing. Row 2, I'm dividing by negative 2. Now I'm taking row 2 and subtracting that from row 1. So a 0 here, this doesn't change, so that's negative 2 minus 1 for negative 3. Okay, this tells us that z equals 1, y equals 1, and x equals negative 3. If you didn't like doing it like that, you could have started from this point here. And let's go this way for now. So if you didn't want to make it into reduced row echelon form, you could have done it from just upper triangular or row echelon form. We get the same z equals 1 from the bottom equation, then negative 2y minus z equals negative 3. But since z equals 1, negative 2y minus 1 equals negative 3, or negative 2y equals negative 2, or y equals 1. And lastly, I'm just going to come to the left-hand side for this. We have x plus y plus 3z equals 1, or x plus 1 plus 3 equals 1. So x plus 4 equals 1, subtract 4 from both sides, gives x equals negative 3. So those are two separate ways of solving the second half of this problem. So writing our answer as an ordered triple, we get negative 3, 1, 1. Now for part 3, we want to check the solutions in all three equations to make sure nothing was wrong. So we're just using the original equations. So 3 plus 1 plus 3, well, that equals, negative 3 plus 1 plus 3 equals 1. So that checks out. Negative 3 minus 1 plus 2 equals negative 2. And then negative 3 plus 1 plus 4 equals 2. So that checks out. It's always a good idea to double check your work on these things because there's a lot of steps in the middle of it. Okay, so problem 3, we're going to solve a smaller system, but by using an inverse. So part 1, we want to consider the corresponding matrix equation, AX equals B, and write what A, X, and B are. So A is just the coefficient matrix, so that's 2, negative 1, negative 4, and 1. So that's just from the coefficients of the left-hand side. X is the variable vector, so we're just going to do X and Y here. And B is the solution space, or the solution vector. So that's 1, negative 1 as our vector. So we can write this as AX equals B, because if we actually multiply these out, A times X gives us the system at the top. It's just a different way of writing it. So part 2 says find A inverse, show work and simplify. So to find A inverse, we are going to augment A with the identity matrix. In the last problem, we augmented A with the solution space. That's to solve the problem itself. Here we're going to augment it with the identity matrix. So I'm going to say 2, negative 1, negative 4, 1, and then 1, 0, 0, 1. Okay, and here we are going to just use row operations to make the left-hand side the identity matrix. So here, let's say row 2 is row 2 plus 2 row 1. So row 1 isn't changing, so that's 2, negative 1, 1, 0. I'm adding 2 row 1s to row 2. So that gives me a 0 here, a negative 1 here, so 1 minus 2 is negative 1, 2, and 1. Okay, let's see. Now let's take the negative of row 2. Or, let's see. Here, I'm actually going to take row 1 is row 2 minus row 1. And then row 2 is just negative row 2. So I'm subtracting row 1 from row 2. So 2, 0, then 1 minus 2 is negative 1, 0, minus 1 is negative 1. Then row 2 is just going to be the negative, so 0, 1, negative 2, and negative 1. And then the last step is to say row 1 is 1/2 row 1. So that's 1, 0, 0, 1 on the left-hand side. Then negative 1/2, negative 1/2, negative 2, negative 1 on the right-hand side. This tells us that our inverse matrix is negative 1/2, negative 1/2, negative 2, negative 1. Okay, so for part 3, we want to compute A inverse A. This question is more to make sure you did everything right. A inverse A should always be the identity. So this should just be the identity here, 1, 0, 0, 1. It is a good idea to double check though by actually carrying out the multiplication. So negative 1/2, negative 1/2, negative 2, negative 1, times 2, negative 1, negative 4, 1. So let's see. 2 times negative 1/2 is negative 1, plus negative 1/2 times negative 4, so plus 2. Then negative 1/2 times negative 1 is 1/2, negative 1/2 times 1, there we go. 2 times negative 2 is negative 4, and negative 1 times negative 4 is 4, negative 2 times negative 1 is 2, and negative 1 times 1 is negative 1. So once we simplify this, we get the identity. So these guys cancel, and then we get 1 and 1 in the corners. So that's what we wanted. If we didn't get the identity, then we would know that we did something wrong, and we would go back to part 2 and double check everything. Okay, part 4, use A inverse to solve the system, and write your solution as an ordered pair. So originally we have AX equals B, as noted above. Then if we multiply on the left by A inverse, we get A inverse AX equals A inverse B. But A inverse times A is the identity, which is basically 1 for matrices. So we get X equals A inverse B. That means to solve this, we just need to multiply A inverse and B together. So we have negative 1/2, negative 1/2, negative 2, negative 1, times 1, negative 1, equals, let's see, negative 1/2 times 1. So that's negative 1/2 plus 1/2 is 0. And negative 2 plus 1 is 1. So that gives us the solutions 0 and, let's see, negative 2 plus 1 is negative 1. 0, negative 1. Okay. You can go up and just double check those. 0 minus negative 1 is 1, and 0 plus negative 1 is negative 1. So they check out as well. Okay, so problem 4, given the following matrices, perform the required computations. Write D and E if it does not exist. So 3A minus D. So let's see, 3A is just multiplying each of the entries of A by 3. So that's negative 12, 3, sorry, a little bit ahead. Negative 9, 3, 12, minus negative 3, 6, negative 2. So we're just going to do these entry by entry. So this means it's negative 9 minus negative 3, 3 minus 6, 12 minus negative 2. Well, we can simplify that. Negative 9 minus negative 3 is plus 3, so that's negative 6. Let's see, 3 minus 6 is negative 3. 12 minus negative 2 is 14. Okay, D times A. So let's see here. -3, 6, -2 times -3, 1, and 4. And remember, to multiply it, the columns of the first matrix has to be the same as the rows of the second matrix. So the first matrix is a 3 by 1, so the 3 rows, 1 column. And the second matrix is also a 3 by 1, so 3 rows, 1 column. So to multiply, these two have to be equal, which they are not, so we cannot multiply them, so it does not exist. Okay, then C times A, -2, 1, 0, 4, 3, -2, times -3, 1, 4. So this is a 2 by 3 times 3 by 1. So since these two are equal, then the result will be a 2 by 1 matrix. So to multiply, we multiply the entries of the row with the entries of the column. So that's -2 times -3 is 6, plus 1 times 1, plus 0 times 4. Then 4 times -3 is -12, plus 1 times 3, plus -2 times 4. So this gives a 7, and then 12 plus 3 minus 8 is like -17. Okay, and B squared. Let's see. A lot of people, when they square a matrix, they're tempted to square each entry. That's not true. Or B, anything squared is just that thing multiplied by itself. So B squared is actually -1, 3, -2, -5 times itself. -1, 3, -2, -5. So we can only square matrices. So it's a 2 by 2 and a 2 by 2. So these two are equal. So the result is going to be a 2 by 2 matrix. So here, -1 times 1 is 1, plus 3 times -2. Then -1 times 3, plus 3 times 5. Then -1 times 2, plus, there's a negative right there, plus -5 times -2. And then -2 times 3, plus -5 times -5. And simplifying those, that gives me 1 minus 6 is -5. -3 minus 15 is -18. 2 plus 10 is 12. And -6 plus 25 is 19. Okay. Let's see. Problem 5. This is sections 7.1, 7.2 now. Identify each sequence as arithmetic, geometric, or neither. Fill in circle to your left. So remember, if it's arithmetic, then there's a common difference. If it's geometric, there's a common ratio. And if it's neither, well, then it's neither. So if there's a common difference, then we're adding the same number between them. So to get from 4 to 7, that's plus 3. To get from 7 to 12, that's plus 5. So that means it's not arithmetic. Let's see. To see if it's geometric, we see like what do we multiply to get to 7. So 4 times what equals 7? 4 times 7/4 equals 7. Then 7 times what equals 12? 7 times 12/7 equals 12. And since 7/4 does not equal 12/7, it's also not geometric. So we'll say it's neither. Okay, part 2. We have 1, -1/2, 1/4, -1/8, 1/16. Definitely doesn't look like it's arithmetic, because 1 minus 1/2, 1 to -1/2 is, we're subtracting 3/2, and then to get from -1/2 to 1/4, it's a positive number. We're adding something. It's definitely not subtracting something. To see if it's geometric, let's see. 1 times what equals -1/2? 1 times -1/2 equals -1/2. And let's just see if that works for the next step. -1/2 times -1/2. Well, the negatives cancel, leaving us with 1/4. So it checks out. So it's geometric with the common ratio of -1/2. For part 3, 3 to 7 is +4, 7 to 11 +4, 11 to 15 is +4, so those are all the same. It's arithmetic. The common difference is 4. And for part 4, 2 to 6 is +4, 6 to 18 is definitely not +4, so it's not arithmetic. Or we can say 2 to 6 is times 3, 6 to 18, it's times 3, 18 to 54 is also times 3. So, see, that one's geometric. Common ratio is we're multiplying by 3. Okay, for problem 6. For the arithmetic sequence a sub n, with the first terms 17, 5, -7, -19, and so on, we want to find the common difference. So it already tells us that it's arithmetic, tells us that it's a common difference. So just what's the difference between these? Well, to go from 17 to 5, that's -12. 5 to -7 is -12. That's really all we need to know. So the common difference is -12. Remember, it's so sometimes you'll be confused as whether it's a +12 or a -12. Remember, it's what do we add to it to get the next number, or adding -12 to get from 17 to 5. So if it's decreasing, it's negative. If it's increasing, it'll be positive. Okay, find an explicit formula for the term a sub n, the sequence, assuming a sub 1 equals 17. So a formula for this is a sub n equals a sub 1 plus d times n minus 1. So it says to get to the nth term in the sequence, you start at the first term and add the common difference times n minus 1. So for us, the first term is 17, d is -12, and n minus 1 is just like that. So we can leave the answer like this. We could also simplify it a little bit by distributing the 12, giving us -12n, so plus 17 plus 12, or -12n plus 29. Either of them work. I'm just going to write it as 17 minus 12 n minus 1 for now. So 6.3 says find a sub 101. Well, we already have the formula for it. Now we just need to plug in 101 into the formula. So A101 equals 17 minus 12, 101 minus 1. or 17 minus 12 times 100. So that's 17 minus, what is that, 1,200, which is negative 1,100, is that 83? Just double check. Yeah, there we go. So that's negative 1,183 is the 101st term. Now technically you could go from the original sequence and just subtract 12 101 times until you get to that term, but doing it with the formula is much easier and is actually doable in the time allowed. Let's see, and lastly we have compute the sum, summation from n equals 1 to 4 of 2n minus 1. So here we can actually just, we don't have to use a formula for this one since it's only up to 4. We can just plug in n equals 1, 2, 3, and 4. So that's 2 minus 1 plus 2 times 2 minus 1 plus 2 times 3 minus 1 plus 2 times 4 minus 1. Or that's 1 plus, let's see, 4 minus 1 is 3, plus 6 minus 1 is 5, plus 8 minus 1 is 7. Well, let's see, that's 10, 16. Okay, let's see. Another way we could do it, let's see. So we could say that, okay, let's go like this. The summation of 2n minus 1 equals the summation of 2n minus the summation of 1. So I guess this is from n equals 1 to 4 equals 2 times the summation of n equals 1 to 4 of n minus, if we're just summing 1 from 1 to 4, well that's just 4. And then the formula for summing n is going to be, in this case, it's n times n plus 1 over 2, where n is just, oh, made a mistake here too, 2, 4, where n is just what we are summing to. So let's see, that's, looks like these twos can cancel, so 4 times 5 minus 4, 20 minus 4 equals 16. So there are times when using the formula, the way 2 is easier, but since there are only 4 different things that we're adding, number 1 is easier for this one. And that is all we have for this exam. So yeah, good luck on the test.